Hello, everyone. I'm Neng Shi from the Ohio State University. I'm glad to present our work entitled VDL-Surrogate, a view-dependent latent-based model for parameter space exploration of ensemble simulations. Scientists usually run ensemble simulations given different input parameters to perform parameter space analysis. As you can see, scientific visualization is a very useful tool to help scientists explore the simulation output efficiently and intuitively. However, the simulation space exploration requires exhausting the complicated parameter space by running a batch of computationally expensive simulations. To make the parameter space exploration more efficient, scientists would exploit surrogate models to mimic the original expensive simulation model. Existing surrogate model-based parameter space analysis in our visualization community usually are either data-based, such as our previous work NNVA, or image-based, such as our previous work in InstruNet, which leads to their corresponding limitations. First, for this data-based method, it is difficult for them to produce high-resolution simulation output. Second, image-based surrogate models visualize the generated simulation data with several predefined visual mappings, so that scientists are not able to adjust the setting of visual mappings to find features of interest after the models have been trained. In this work, to solve the two limitations mentioned above, we present a surrogate model exploiting representations that are, first, view-dependent latent, such that it can support visualization of high-resolution simulation output. Second, not dependent on predefined visual mappings, so that the surrogate can support visualizations with different visual mappings. In the next slide, I will further clarify the first point, that is why we use view-dependent latent representations. As I mentioned before, the key of our work is to use view-dependent latent representations. First, I'm going to explain why a view-dependent strategy is necessary. Look at the right figure. Imagine that we have a very high-resolution simulation output. In that case, we may not want to visualize it with its raw data resolution, because that is not necessary at all. Instead, our visualization surrogate may produce output with the desired image resolution, but focus on maintaining the quality of the simulation output along the view direction. It is not hard to imagine that after applying this strategy, there would be some savings of our method. Second, we'll explain why we need a latent instead of just applying view-dependent approach alone. This is because if we use the view-dependent approach alone, the GPU memory constraint still does not allow us to train the surrogate model successfully. That is why we use latent representations along the view direction to further improve the model efficiency. Next, I'm going to start present our method. First, I'll give the audience an overview. Note that the training phase of VDL-Surrogate is composed of two stages, view-dependent latent generation and VDL predictor training. And there are two major networks in the pipeline. The first one is called Ray Autoencoder, abbreviated as RAE. The second one is called View-Dependent Latent Predictor, abbreviated as VDL Predictor. Before diving into the details of the two training stages, note that our view-dependent latent representations are generated given a selected viewpoint. And in our work, we select the three view directions parallel to three main axes and generate view-dependent latent representations for each ring direction. This slide describes how to generate the view-dependent latent representations that are later used for the downstream predictor training. Note that this step would help reduce the computation and the memory cost of the predictor training. Now let's start looking at the pipeline. For a full resolution simulation output, given a billing direction, We sample it via interpolation to obtain view-dependent data. Next, with the view-dependent data, along the view direction, we cast the rays parallel to the view axis and collect the ray samples. Then, the ray samples are encoded by the RE encoder to ray latent representations, and decoded by the RE decoder to reconstructed ray samples. For the details of the RE structure, please refer to our paper. Next, we describe the video predictor training. After RE is trained, we run more simulations and perform view-dependent sampling on these simulation outputs. And for these new view-dependent data, we encode them in situ for latent representations. Then, with the pair of input simulation parameters and its corresponding view-dependent latent representations, we train a convolutional model called the video predictor to then learn their mapping. As well, for the details of the video predictor structure, please refer to our paper. In the inference stage, as illustrated, for a selected viewpoint, we first feed the unseen input parameters to the trained video predictor and generated the predicted view-dependent latent representations, which is then sent to the trained RE decoder and decoded back to the data space. Note that our final goal is to generate the visualization result from an arbitrary viewpoint. Look at the Villing sphere. For an arbitrary viewpoint V, we would cast rays to sample the 3 predicted view-dependent data generated from previously selected viewpoints. And at one ray sample location, we average all the 3 sampled values by inverse viewpoint distance weighting, such that the sampled value from a closer viewpoint should contribute more than that from a more distant viewpoint. We evaluate our method using 2 simulations for different scientific applications. In the following slides, I will show qualitative evaluation and parameter space exploration. For more results, please refer to our paper. Qualitative evaluation. First, for the next dataset, we predict the visualization images of the log density field from a sequence of different viewpoints. As you can see, VDL-Surrogate generate high-quality visualization images without popping effect when changing viewpoints, compared to the baseline method in SearNet. Next, for the MPath Ocean dataset, we predict the visualization images of the temperature field from a sequence of different viewpoints, and we have similar observations. Parameter space exploration. First, for the next dataset, we fix other simulation parameters and sample the simulation parameter Hubble constant h from 0.55 to 0.85. From the 2 images rendered with different transfer functions, we find that the high-density region becomes smaller as Hubble constant h increases. Second, for the MPath Ocean dataset, we fix other simulation parameters and sample the simulation parameter BWSA from 0 to 5. As shown in the left part, the sea level temperature map, when the BWSA increases, the blue stripe in the image becomes more evident. In the right part, from the visualized 3 isothermal surfaces, we can see that the surfaces have a higher curvature when BWSA increases. Talking about the performance, after training, a forward pass through our trained video surrogate takes less than 1 minute, instead of the roughly 1 hour it would take to directly compute the simulation output on a large cluster of CPUs. In conclusion, we propose VDL-Surrogate, a view-dependent neural network latent-based surrogate model for parameter space exploration of ensemble simulations that allows high-resolution visualizations and user-specified visual mappings. We demonstrate the effectiveness and efficiency of VDL-Surrogate by comprehensive quantitative and qualitative evaluations on cosmology and ocean ensemble simulation datasets. Thanks for listening. We also thank our funding providers. Now I can take some questions.